Okay, so we're going to continue on here with acids and bases. Last time we talked a lot about pH, the pH scale, how to calculate H plus concentrations. So we did see a number of different sort of formulas. We started with Kw, right, which is our H plus and our OH minus concentration equals 1 times 10 to the minus 14. Again, if we're just given the H plus or the OH minus concentration, we obviously could use this to calculate the other. We could also compare the two concentrations as we did in some problems and determine if it's acidic, basic, or neutral. Obviously, in this case, if the H plus is larger than the OH minus, it's acidic. OH minus larger than the H plus is basic. And if they equal each other, then it's neutral. We then talked about kind of the pH scale. The pH scale again goes from 0 to 7 to 14. Again, below 7 is acidic, above 7 is basic. And because when these two guys equal each other, you get 1 times 10 to the minus 7. 7 is going to be neutral. As we talked about, 7 sort of your midpoint there. As you go closer to 0, you become more acidic. And as you go closer towards 14, you become more basic in that case. We could calculate the pH by taking the pH is equal to minus the log of the H plus concentration. Again, the name tells you what you need. You need the H plus concentration. We also talked about a scale that's similar to pH, but measures the OH minus concentration, and that is the POH minus the log of the OH minus concentration. The nice thing about both of these are if you take the pH plus the POH, that does equal 14. So that does give you a little workaround in certain cases as to how you can solve some of these problems. We also saw that if you did have the pH, you can get the H plus concentration from it by taking the inverse log of the minus pH. Again, as we talked about on most people's calculators, that is the button above log, which is the 10 to the x, and usually you have to hit the shift or second button to do that, and usually that will pop up like a 10 and a caret on your calculator, and then usually you'll do the negative pH. We could do a very similar calculation with POH. From the POH, we can calculate the OH minus concentration. It's the identical calculation. It is the inverse log of the minus POH. And again, on your calculator, probably will do like a 10 and a caret POH. As we talked about, this really does give you a sort of options as how you can solve some of these problems. There's really no wrong way as long as you choose sort of a legitimate way to do it. They all really should give you the same sort of answer when it's all said and done. Any questions on that stuff there from last time? Now, we also saw really at the very end, sometimes you're not just given like a generic H plus or OH minus concentration, but you may be given a strong acid or a strong base and want to know what the pH is. When you have a strong acid or a strong base, they're both strong electrolytes, which means that they will 100% break apart. And obviously, like something like HCl, when it breaks apart, you get H plus and Cl minus. It is the H plus concentration, which is obviously important to calculate the pH. When you have a base, remember though that, you know, if you do have a base or even an acid, and we do break apart, say into hydroxide, which I think is the one we did at the very end there, we do need to take into account the 2 here in terms of the concentration so that we do get the correct hydroxide concentration. Obviously, because it's a base, we would go probably the POH route first, subtract 14 there, and get yourself to the pH at that point. Any questions on any of that stuff we talked about? So how do you know if it's a strong acid or a weak acid or a base? Here's again a table, some strong acids and strong bases. These are your common ones: perchloric, hydrochloric, hydrobromic, hydriodic, nitric, and sulfuric acid. These are very common strong acids. Our strong bases, as we might have mentioned, I think the other day as well, really do come from group 1 and 2 on the periodic table that has hydroxide in the actual formula. And basically, if you just kind of come down, this is basically going down group 1, and then you hang a right to basically group 2 and go down. All those guys that have hydroxide will be obviously strong bases. So if you're given any of these guys here, obviously you would do the same approach. You want to get the correct H plus concentration or correct OH minus concentration to allow you to get to the pH. Remember as well that one important thing and a very common mistake that people make is when they are asked the simple question of, is this solution acidic, basic, or neutral? Sometimes people will give multiple answers for that. And that's because they calculate the pH and the pOH. And as we talked about, I think last time, they'll look at the pH and go, oh, cool, it's above 7, it's basic. Then they'll look at the pOH and go, oh, it's below 7, it's acidic, and that's the same solution. So remember, always look at the pH value. That is usually the scale that you have in your head. Remember, the pOH scale actually runs opposite of the pH scale. So if you have a high pH, you got a low pOH and vice versa. So they do run opposites of each other. The other important relationship to remember is, right, that H plus and OH minus also run opposite of each other. So as one goes up, the other goes down. So as we increase the H plus concentration in the solution, OH minus gets lower, and vice versa. If we increase the OH minus in the solution, the H plus concentration goes down as well. So we've talked now about how to handle, obviously, strong acids and strong bases. Clearly, weak acids and weak bases are handled differently because they're weak electrolytes. They mainly stay together in solution. They do produce a little bit of H plus and OH minus. So we do get actually an equilibrium that occurs because it is a weak acid. HA is, by the way, just a generic formula you can use for an acid if you ever need one and you don't really give you a formula. HA is a monoprotic acid, meaning that it has one H to give. If you had H2A is a diprotic acid, has two H's to give. And if you had H3A, that would be like a triprotic acid. So sometimes they may just talk in general terms and not really give you a specific acid. So those are some formulas you can use. You might remember that maybe from your titration experience in 200A. You had a monoprotic, diprotic, or triprotic sort of acid that occurs. So if we look at a weak acid, because it mainly stays together but does break apart, it does create a reversible reaction, which means we could really just and take it to this equation. And because of that, we can write an equilibrium expression like all of our other equilibrium expressions. We're going to take our products over our reactants. So in this case, it would be H plus times A minus divided by HA. And this is known as Ka. I'm assuming A means acid. I never really asked, but I'm assuming that's correct. So that is a Ka value. It is used for a weak acid. It is still an equilibrium constant. So it's just like all the other ones, Kc, Kp, all the other ones we talked about is still basically our products over reactants. But again, Ka here is our equilibrium constant. When we have a large Ka value, the strength of the weak acid actually increases. That is because when we have a large K value, when I reach equilibrium, do I mainly have reactants or products? Products. What makes something an acid is the ability to produce H plus, basically, right? Or H3O plus, which means if I have a large Ka value, I have more products. More products mean I have more free H plus in the solution or H3O plus in the solution. And that would make it a stronger weak acid. That does seem contradictory there. So when we're talking about a strong weak acid, we're talking about in comparison to other weak acids, it would be stronger when the Ka value increases. Something that is a straight up strong acid is much stronger than obviously this. The reason it is much stronger, right? A strong acid versus a weak acid is a strong acid is a strong electrolyte, 100% breaks apart, which means pretty much it just needs to go for a swim and you just produce a lot of free H plus really quickly, right? And that's a pretty good acid. Here, this weak acid is going to mainly stay together, but produce a little bit of H plus. So because it's still able to produce H plus, it's considered an acid. but it will not produce anywhere near what a strong acid would contribute to the solution. Do we have Ka values for strong acids? The answer is no, we do not, because it is a equilibrium constant and strong acids is a one-way street, right? There's no reversible. So because it's not a reversible reaction when we're dealing with a strong acid or even a strong base, when we get to those, we don't have Ka values. So that's a very giant hint when you're doing a problem. If you find a Ka value on a table or you're given a Ka value in the problem, you are dealing with a weak acid problem, right? So that's a pretty good way to kind of remember that. Any questions on that there? So here's a table, and you have a similar table in your book of many different sort of weak acids. And again, if you could find obviously a weak acid on this table or a table like this, then definitely our Ka value definitely is a weak acid. The only one that technically you will find the sort of a strong acid typically on a Ka table like this. Let me see if I can find it. I don't know if it's on this one. You will sometimes find the guy that comes before this guy, which is sulfuric acid occasionally on it, but usually they will not give you a value. They'll just say it's very large, which is not very helpful in normal cases. You will find sulfuric acid occasionally on the table that will say very large, not really give you a number. And the reason for that is a diprotic acid, which means the second part of it actually acts as a weak acid. So that's why you'll sometimes see it on the table. But usually, again, anything that is strong will not have a Ka value. Anything that is weak will. And you may have to reference a table, obviously, to figure it out or to solve a problem. How do we solve these problems? Because they are weak acid problems and they're really an equilibrium problem, we need to solve these basically doing an ice table. So we do pretty much the same type of ice tables we did in the previous chapter. The main difference is we're usually interested in this case about the pH, which means, you know, although we will solve a lot of times for all the equilibrium concentrations, we really want the H plus concentration at equilibrium. Once we get the H plus concentration at equilibrium, we then do one additional step, which is put it into the pH equation and calculate the pH. So these are worked exactly the same way. You solve them pretty much exactly the same way. The only difference really is you're interested in the H plus and you want to go into the pH equation at the end. So with that being said, why don't you give this one a go here and see what you come up with. See how you're progressing here. So first off, you know, it's always good to think about the problem, think about what information is given to you. Sometimes people really overlook like all the stuff in the actual problem. So clearly, if you have no clue what's going on, I hope that's not the case, by the way, but in case you don't, you know, you look at this problem, a couple of things should really point out to you. Clearly, I see a Ka value. So even if you had a question, that should obviously tell you that this guy is a weak acid. It should also tell you that since it is a weak acid, I gotta probably do like an ice table would be a pretty good approach there. So, you know, there's a lot of information inside these problems that, you know, sometimes people just kind of overlook and jump in. So always kind of take a look at the problem and it can kind of point you sometimes in the right direction. So obviously I now know this is a weak acid. I know it's going to be a reversible reaction. I know I'm going to need to do an ice table. So that's pretty much my starting point here. I'm going to write the proper equation here, which is my hydrofluoric acid going to break apart into H plus and F minus. Now, obviously, if you wanted to, you could write HF plus water and you would just get H3O plus on the other side. Perfectly fine, whichever way you want to do it. We're going to go initial here. The only thing that's given to us is the 0.5 molar of our HF. Just like we did previously, in this case, since they don't say anything about rate products, we could safely assume that we're starting with 0 of everybody on the right-hand side. In addition, because of that, we could also pretty safely assume that the reaction should be heading towards the product side in this case. And that makes the change part pretty straightforward. It's going to be minus X, plus X, and plus X. That means when we reach equilibrium, we will have 0.5 minus X, X, and X. Any questions on the ice table there? Also, obviously, because it's an equilibrium constant given to us, we might want to write the equilibrium expression, which should be Ka is H plus times F minus divided by our HF. And that obviously equals right there our 7.1 times 10 to the minus 4. Just like normal, we're going to take our equilibrium line and put it into that expression, and we want to solve for x. So basically, if we do that, we will end up with x squared up on top. We'll end up with 0.5 minus x, and that will equal our 7.1 times 10 to the minus 4. Now we want to solve for x, and of course we want to, not take all day to do it, perhaps, right? What can we do here? Our equilibrium constant is large or small? It is small, which means just like in the previous chapter, we can make an assumption here, and we can assume that x is equal to 0 because our equilibrium constant is small. And again, as a reminder, we're pretty much only zeroing out any x's we're going to be subtracting from or adding to. So that's pretty much this x right here. When we do that, we will end up with x squared divided by 0.5 will equal 7.1 times 10 to the minus 4. Now we're going to solve it. I'm going to multiply the 0.5 to the other side. I'm also going to take the square root of it afterwards. So that's going to take 0.5 times 7.1 exponent negative 4. Going to do a little square root action here, hopefully. There we go. And that's going to give me an x value, again, after multiplying and taking the square root of 1.88 times 10 to the minus 2 in this case. Yes, sir. It is products over brackets, yeah. These are products. That's okay. Yeah, so it should be, you're right, it is products over reactants. Our H plus and F minus are on our product side, and our HF is on our reactant side. Yeah. No worries. Other questions? Now, the other important thing is when we do make an assumption such as this, we should always check it, right? So we should make sure that we do check it. Remember, we're going to roll with the 5% rule because why not? So what that means is the way that we check it is we take the x value we just got, and we basically divide it by what we're going to subtract it from, which in this case would be 0.5, times it by 100. And if we are 5% or less, we are in business, which I think we're in business on this one. We are at 3.77. I'll take it. 3.8. That works. So because we are less than 5, our assumption is okay to use. And again, in this case, sort of where we will also deviate from what we did before, we're really only interested in the H plus concentration so that we could get to the pH. And we can see from our table that the H plus concentration actually equals X. So that means that the concentration of H plus at equilibrium, which is when you'd want to calculate your pH from, would be equal to X, which means we got like 1.88 times 10 to the minus 2 molar. That now is good to go right into our pH minus the log of 1.88 times 10 to the minus 2. And that would give us a pH here for this acid of something. Looks like a we'll call it 1.73, which is acidic. So that's good. And that makes sense. It's not basic. Any questions on any of those steps? So it is pretty much identical. Most of the calculations we do will be similar. There are some slight variations that you got to do. But here again, we can calculate the pH by getting the H plus concentration. Any questions on any steps? Yes. Yeah, you got multiplied by 100. Divided by 0.5, yeah, times by 100. Other questions on that? Now, remember that as we talked about in the previous chapter, you should always check it because not always going to work, your assumptions. So, for example, if we did this exact same problem, except that the concentration was a little bit different here, if we ran through our ice table, really the only difference here is going to be our initial concentration, which is 0.0500. We'll get the same minus x plus x plus x. We will get 0.05 minus x, x, and x. We would go into our equation of x squared. 0.05 minus x is equal to 7.1 times 10 to the minus 4. We would assume that x is equal to 0. And when we do this guy, it gives us something like this. Doing the same thing, multiplying to the other side and also taking the square root here. We end up with an x value of I'll call it 96 times 10 to the minus 3, which upon dividing by 0.05 and timesing by 100% in this case, gets us approximately 12%, yes, which would make us be very sad at this point, yes. So you want to not just get into the habit of just assuming that the assumption will always work. Make sure you do take the time to check it. Otherwise, remember, in this case, we would have to go back really and probably do a quadratic formula and solve it this way. So again, just a reminder, it will not always work. Reason it doesn't work here is because, as we'll talk about in a bit, concentration is very different, right? So if you have a large concentration to start with and you lose a little bit, that's not a lot, right? But if you starting with a very small amount and lose a little bit, that is a lot. I like to use the pizza example, brand new pizza, take one slice, not a big deal. Pizza down to 2 slices and take one, kind of a big deal at that point, right? Not a lot left. It's a bigger proportion of what you started with. And it's the same idea here with concentration and whether or not the sort of assumption will work. The initial concentration is relatively important on that. Any questions on that there? Yeah. Yeah, so it's relative in a couple of things. It's relative obviously to also the equilibrium constant that you're dealing with as well as to whether it's on a large or a small value. But yeah, it can have an effect, your initial concentration. Again, typically if you have a larger one, relative, if you lose a little bit, not a big deal. But if the concentration is really, really small, we'll talk about in a little bit in this chapter, is what's sometimes referred to as percent I'm going to say that right, percent dissociation, basically how much basically will come off for the acid. And again, if you're just starting with a small amount and lose a little bit, it's going to make a much bigger deal than if you started with a larger amount. Other questions on that? Okay. So as we saw in these problems here, pretty much the same deal. We're just going to do our ice tables whenever we're dealing with a weak acid. We can ignore the autoionization of water, and what that means is, and I think your book does ignore it, and most people do ignore it. There are certain situations where you calculate, for example, the H plus concentration or OH minus concentration, and they'll go, well, the concentration of water of H plus and OH minus is much larger, so we'll look at water's contribution to it. Gets a little confusing when that happens. So we will ignore really, sort of water's contribution to H plus and OH minus. We will assume in most of our problems here that all of the H plus and OH minus that we see will come from the weak acid or weak base. In that situation, water is not necessarily providing anything. Again, the key here is we want to solve for X. We can do any method like we've done before. The additional step is putting that into your pH equation. So it's given everyone a go here. What is the pH of a 0.122 molar monoprotic acid, whose Ka value is 5.7 times 10 to minus 4. Again, you could use this formula for just like a generic acid. Okay, so since we're getting to the end, let's take a look and see how we're doing. So again, you can use HA if you're not really given a particular acid. We again have some information here that helps us understand what we should be doing. We see a Ka value. So we definitely know it's a weak acid. Again, we should be doing our ICE table. So we'll start with our dissociation equation here, which is our weak acid, which will dissociate into H plus and A minus. We could also write our Ka expression, which would be our H plus times A minus divided by our HA. And that obviously would equal our Ka value that's over here. We can do our initial concentration here of 0.122. Just like the previous ones, we are not given any information about our product. So again, safe to assume 0 on those guys. Change again, we could also know that the direction should be heading to the product side. So that will be minus x, yielding us at equilibrium 0.122 minus x, and x at this point. Any question on the ICE table there? So rolling through like we did before, we're going to take those guys, we're going to put it into our expression here, giving us 0.122 minus x. And again, that will equal what was given to us, 5.7 times 10 to the minus 4. You could assume x is equal to 0. Is it good? If you didn't check, you should have, because it's bad. It's like 6.8% here. So the assumption does not work in this case. So again, you want to make sure you do check it. May not make a giant difference in the end result, but sometimes it will. But for our purposes, it will make a big difference because you should have checked it. Yes. So in this case, it is actually 6.8%, which is larger than obviously 5%. So we do need to go back really and solve it. So we're going to solve it by, again, bringing everybody here to the other side and combining all of our terms. When we do that, we will end up with an x squared is equal to 6.95 times 10 to the minus 5 minus 5.7 times 10 to the minus 4x. Bringing everybody back to the same side gives us an x squared plus 5.7 times 10 to the minus 4x minus 6.95 times 10 to the minus 5 is equal to 0. At this point, we will put it into our quadratic, which is our x is equal to our minus b, which in this case would be minus 5.7 times 10 to the minus 4, plus or minus the square root. If you clean up everything inside the square root, you end up with 2.78 times 10 to the minus 4. Then if you take the square root, you end up with 1.67 times 10 to the minus 2 when you do that. We're going then divided by 2 times a, which in this case is 2 times 1, which would be 2. Taking the negative and also taking the positive, we end up with our 2x values here. X would equal 8.07 times 10 to the minus 3, or a negative 8.64 times 10 to the minus 3. Any questions on that part of it there? Clearly, because we're interested in pH, and we see that H plus equals X, the one that we should not use is the negative, right? Because obviously that's not going to end up well. That means that this X that we got over here on the left should be the H plus concentration. So we'll put a little molar on that, and that will equal the H plus concentration. That means that's really all we need to go into the pH at this point. The pH here minus the log of 8.07 times 10 to the minus 3, going to yield us a pH of 2.09 in this case, which will be the correct answer, not 2.08 by doing the assumption, yes, or 2.07 depending on where you're rounded by doing the assumption. In this case, not a big difference, but in a lot of problems, there is a big difference between doing the assumption and not doing the assumption. So you do need to make sure you check it. Again, a good reminder to make sure that you do. A lot of times the assumption will work, but it is well worth taking the extra minute or so there just to make sure that it's okay and that you don't have to go back and actually do it a different way. Any questions on this here? Also makes sense. It's an acid. We got an acidic pH. So again, these are things we want to think about. If you at the end of this ended up with a basic pH, something definitely went wrong in this particular problem. Any questions? Okay, we will stop there today.